Hello, everyone. This is Jianjun. In this talk, we will present Krypton, real-time serving and analytical SQL engine at ByteDance. This is joint work with many colleagues in ByteDance. The motivation for our work is that many of our customers require performing real-time data serving besides complex ad hoc analysis over large amounts of freshly imported data. There are several typical data serving use cases in ByteDance. The first one is to compute real-time statistics, such as the number of likes displayed in real time. Second is real-time user profiling. For example, to compute the top N clicked item in the last 10 refreshes for each user. Third is real-time model training and learning. For example, we aggregate real-time signals, such as payments and user clicks, to continuously derive user statistics, which are heavily used in online and offline training. There are major differences between OLAP and data serving requirements. For the OLAP use case, data changes are relatively infrequent, and the data freshness are typically in the like hours or even days. Query latency typically at like second level, and the query QPS normally like in the range of like tens and like hundreds. Query can be complex and arbitrary. In the data serving case, however, we can see like a customer may want like millions of like new rows got ingested every second. Data freshness can be like sub-seconds. Query latency can be like milliseconds, and the query QPS is much higher, typically like maybe like between 1,000 and even like millions. Queries are, however, much simpler, and more importantly, they are often predefined. That provides good opportunity for pre-computations. So in order to work around like the bigger gap between these two requirements, customers often forced to use multiple systems together in production. That brings following drawbacks. So the same data have to be ETL'd into multiple systems. That causes like a data consistent problem. It also causes like a waste resources, and also it puts more burden on customer for higher learning and maintenance costs. So our goal is to build a single system that can handle both OLAP and serving workloads. The design goals for Krypton include standard SQL support, larger scale, low query latency, high QPS, strong data consistency. In specific, customer wants to have a consistent snapshot reads and atomic writes. We also want to provide a greater data freshness and high ingestion rate. HSAP is still kind of a new concept, and only few systems on the market yet. So far we know a couple systems fall into this category. One is Google Procella, and another is Alibaba Holograph. This slide shows the Krypton architecture. So Krypton adopts like a disaggregated storage architecture. It also separates the read and the write query processing to provide a great isolation and elasticity. So from the diagram, you can see for to handle like a data streaming data ingestion. So the data got basically input come into our ingestion server. Then it will basically put the data into the data store, flush to the Warlog, and eventually the data will be flushed to CloudStor. So for the read pass, the queries will come to our coordinator, which generates the query plan, and the query plan get sent to the data servers for like MPP type kind of query execution. So the data will be loaded from data store to the data server. Because we have this disaggregated storage, in order to improve the query performance at data server, we maintain a local cache. So besides like a streaming data load, we also support a batch data load that will load data directly into CloudStor. The system also contains a metadata server that provides global metadata, and also a compaction server that does data compaction for the data stored in CloudStor. So in summary, on the right side of the slide, we summarize the important principle for the system design, disaggregated storage, and separate the reads and the writes, MPP query execution with hierarchical cache at the data server. We want to emphasize that our system heavily utilizes cache and the pre-computations for providing good query performance, especially in the data serving case. Also, it's important that we provide a customizable configuration so that customers can choose based on the cost, data freshness, and the performance trade-off to basically to configure their system based on their requirements. So for data ingestion and the pre-computation, as I mentioned in the previous slide, so our system supports like a streaming mode and the batch mode data loading. Okay, so besides the base table, Crypton also supports aggregated table and the materialized views for pre-computations. So this aggregate table and the materialized view are maintained in real time during data ingestion. Table stats like a table row count and NDV are incrementally maintained automatically by the system. Preloading option can be configured at the table level so that data can be preloaded into the data server cache once they are ingested. Crypton adopts adaptive query processing. First, it's uses adaptive statistics with dynamic sampling. Crypton has a unified cache framework that caches almost everything, including a query plan, query fragment selective estimation, and also query results. So for the stats cache, it has a stats cache with query filters. So at the planning time, QO can issue a sample query to collect the cardinality information. Also, the system utilizes the actual query execution results information to dynamically update the stored hash entries. It also has an adaptive parallelism control mechanism. So at a planning time, QO can predetermine the parallelism at both inter-fragment and intra-fragment level. At the execution time, query execution has the freedom to dynamically parallelize the computation within query fragment. Crypton also supports the resource isolation and the fair scheduling. So customers can create resource groups so that provide a data server instance level resource isolation. Within a data server, the system can provide a fair scheduling mechanism. It can solve resource contention within a resource group through its core scheduler with a priority-based global time slicing queue. Crypton also provides a special optimization for serving queries. For example, it supports like a dirty read in order to achieve sub-second data freshness. The data server can directly read uncommitted data from the in-memory data store of ingestion servers. In addition, it also provides a lightweight API for single node serving queries. So this API is used for executing simple query on a single DS that basically execute and fetch query results synchronously with a single RPC call. So that can provide a better query latency. Crypton also provides a hierarchical cache. It's basically the cache can consist of like a DRAM, PMEM, and SSD layers to provide a customer good trade-offs among performance, capacity, and the cost. A couple techniques it used to boost the performance. One is uses a NUMA-aware async write mechanism to optimize the PMEM write performance. It also utilizes a zone-based SSD store to provide a great performance. It has a native column data format that supports efficient processing and also storage. It supports lightweight encoding and rich type of index to achieve efficient scans and seeks. It designs an efficient algorithm to represent nested and repeated types. Later materialization and computation pushdown heavily used to reduce I/O overhead. This slide shows experimental results for the resource group isolation. We use YCSB and the TPCH workload to create a synthetic HSAP workload. So YCSB is used to represent the data serving workload. TPCH is for the OLAP workload. So this diagram essentially shows either we run the workload separately or we run them in parallel with the separate resource group. The overall query performance are very similar. So that demonstrates the effectiveness of our resource isolation. This slide shows the experimental results for the fair scheduling. So we create like a mixed workload with like a long query and short queries. So we use TPCH Q21 for represent a long running query and a Q6 for short running query. So this slide essentially tells that with the fair scheduling, even though we increase the number of concurrent Q6 from 1 to 8, the performance for both type of workload are still pretty good. Without the resource, without the fair scheduling, we can see the query 21, the long running query, though the performance can become really, really bad. To conclude, HSAP system can provide the customer a unified solution to handle both OLAP and serving workloads. Krypton can provide excellent elasticity and query performance with great data freshness and strong data consistent support. HSAP still in its early stage, and more academia and industry work are needed. Thank you.